Okay, allow me to say this one more time because my recording stopped for a second. Okay, so we have this function. We create the function from the equation because this is this. So we have the function. We know it's continuous on the closed interval because this is a continuous function, this is a continuous function, this is a continuous function. So I have to write this 3 words as 4 or 5 as a sum or difference of continuous functions on this interval. We plugged it in, f of 0 was negative, f of 1 is positive. Now all I have to say is that from 1 and 2, by the IVT, the intermediate value theorem, I will always find there is always a C, at least one, maybe more, but at least one in the open interval 0, 1, not 0, not 1. So this is open and this is closed, such that f of C is 0. Good. Back to the list. This was IVT. I'd like to talk about this, a simple example in which you will be asked to find the vertical and the horizontal asymptotes. Is that okay? Okay, so I'm going to make one up. So here's a function, x minus 1 over x squared minus 1. So the question for this problem will be something like this. Find all horizontal and vertical asymptotes, if they exist, right? And the limits pertaining to those. So find all horizontal and vertical asymptotes, if they exist, of course, and their limits. I don't care what the question is all about. I'm looking at this function, and I remember factor, simplify, and descending order, no negative leading coefficient. All the time. This should be in the back of our minds. Factor, simplify, descending order, no negative leading coefficient. This is my first step. I don't care what the problem is saying. Eventually I will look. But right now I only can see this function. And when I look at this function, I see something nice. I see that if I factor the denominator, what do I get?
X minus 1 times x plus 1.
Brilliant, thank you. I'm not allowed to touch anything before I state restrictions. So I don't look. I will find the domain, negative infinity, negative 1, union, negative 1, 1, union 1 to infinity, because x cannot be plus or minus 1. After I'm done with this, I will look. Only now I can look. Don't rush. Ah! X minus 1 goes away. I'll make myself a note. X equals 1, hole in the graph. Not a vertical asymptote. Hole in the graph. Now the simplified form is x over x plus 1. This is what I continue to deal with, but the domain is stated for the original function. You can say, but now for this function, x equals a positive 1 is not a DNE situation. I'm sorry, an undefined situation. I don't care. This is the function I'm given. So the restrictions move to this or transfer to this. Okay. So now I know that x equals negative 1 will be a vertical asymptote. X equals 1 is a hole in the graph because the factor disappeared. Factor disappeared. This is a vertical asymptote. Factor did not disappear. That's why this stays as a vertical asymptote. A hole in the graph is when the factor disappears from the top and the bottom. So this one, I don't have to find any limits because I'm not asked to. We will have to find them later on in the next chapter. But I'm not asked to find anything else but vertical and horizontal asymptotes. So I know that this is a vertical asymptote. I have to write the limit as x approaches -1 from the left. And I have to write the limit as x approaches -1 from the right. Of the simplified form. Don't go back to that. That is done and over with. So the numerator goes to -1. The denominator goes to 0. The numerator goes to -1. The denominator goes to 0. But I have to establish the sign of the 0. I can say sign for 0. Yes. -1 from the left is with -1.1. -1 from the right is with -0.9. This is what I plug in and find the sign of the 0. This is what I plug in and I find the sign of the 0 so I can get the answer here. So what do I have? I know it's no hope.
Left is negative, right is positive. Or well, like that one's negative.
But the numerator is negative.
Oh, well, that one's positive and the other one's negative.
Exactly. Positive infinity, negative infinity. So I found the vertical asymptote and the corresponding limits. Now for the vertical asymptote, and now I need to find the horizontal asymptote. For the horizontal asymptote, I have to find the limit as x approaches infinity from x over x plus 1. And it will be the same because this is a simple rational function. How do I do this? Where is the numerator going?
Infinity.
Very good. Sign is not important. Where is the denominator going?
Infinity.
Good. In this situation, what is the procedure for something like this? When we have infinity over infinity, what is the procedure? What do we need to do? There is nothing that I can do to the top, though, because it's already factored. What is the degree of the denominator?
1.
Good, I have to factor it out. It does not matter. I saw some of you are multiplying and dividing by the same thing. It's not a good idea. It's a method, but it's not a good idea. Okay, so I factor out the degree. What do I have in parentheses? I started with 2 terms. I have to have 2 terms.
1 plus 1 over x.
Very good. Okay, this will go away. Please make sure that you're putting 1 and not 0, right? Now I apply the limit operator, it will go away. What is the final answer? In other words, I'm asking, where is this going?
0.
Good. So then what is this?
1 over 1.
Very good. So then y equals 1 is the horizontal asymptote. That's it. That's all you need to do. Good. So we can look at continuity at the point and the gibberish, or whatever else you want. Which one is next?
Continuity at a point.
Good, very good. So let's take a look at a function. I'm going to make one up. I don't know if it's going to work or not. We'll see in a moment. I just made it up. We can look up and we can choose one from the book. But okay, so the question here is find C so that f of x is continuous everywhere on negative infinity to infinity. So for such a question, the first thing I have to write is number 1, 2x plus c, and cx squared plus 4 are continuous as Pauli functions. We know that polynomial functions are always continuous, and that's done. And in step number 2, I have to write continuity at x equals -1. What has to happen at -1 so that this function is continuous everywhere? And that is the definition of continuity at a point. Limit as x approaches -1 from the left must equal the limit as x approaches -1 from the left, from the right must equal f of -1. Tell me, what do I write here and what do I write here?
Or -1.
So 2x plus c, and here
X squared plus 4.
cx squared plus 4. So this is what I have to write first. This is the definition of continuity at a point. Now, can anyone give us this limit? And can anyone give us this limit? And can anyone give us f of -1? The first piece, how much? I'm applying the limit operator, of course.
-2 plus c.
That's it, awesome. Now apply the limit operator here. What do we get?
3 plus 4.
Now f of -1 is specifically where the equal symbol is, which is c plus 4 as well. What has to happen for this? I have to change this because it's not good. See, C disappears. Okay, now it's not going to disappear. Good. So please change the function into, as I said, I was hoping it wouldn't. It didn't need an adjustment, but it does. So 2x plus 2c, or any number, doesn't matter really, as long as it's not 1. Good, so then the limit will be -2 plus 2c, that's correct, c plus 4, and c plus 4. This piece must equal this piece, because these two are already equal to each other. These two have to equal. I'll find c and plug it in. And then I'll say, for this particular c, the function is continuous everywhere.
C equals 6.
Indeed. So -2 plus 2c equals c plus 4. So then c equals 6. I subtract c and add 2. So then my function, the only function, for only one value, just for 6, 2x plus 12 for x less than -1, and 6x squared plus 4 for x greater to -1, guaranteed to be continuous on everything, everywhere. We made it continuous, and only 6 will. So the limit from the left is 10. The limit from the right is 10. The function value is 10. Very good. Would you like to look at it? That's the last topic that I had on my list, unless you want to go back to limits. Do you want to do a gibberish, or the gibberish is clear, or you want to go back to limits, or you want again an epsilon delta?
I have a question.
Yes, anything. Yes.
So do we ever get numbers instead of like the infinity sign? And the guaranteed to be continuous on, can it all be like -1 to 6? Or it has to be like the infinity sign?
No. So for example, this is a typical situation in which we're asked, find C to make this function continuous everywhere. Yeah, this is just a generic example, basically. It only illustrates that we understand the definition of continuity at a point. That's really, so no, you're not going to get some restricted domain. No. If that's what you meant, right?
Yes.
No, don't worry about that. So what are we doing next? Back to the list. We want to look at limits. We want to present an example of a graph. So we also looked at continuity at a point. And we did limits. Is there anything that you want to pick?
Can you please go through the
Yes.
the asymptotes again? The horizontal and the vertical again?
For the horizontal, we only have to determine, so for the horizontal asymptotes, you only have to determine the limit as x approaches infinity and the limit as x approaches negative infinity of the function. That's it. And if you get a number, then you will say y equals that number is the horizontal asymptote. For the vertical asymptote, we are looking at the function. So let's say x approaches a from the left of f of x equals infinity. Then x equals a is the vertical asymptote. So that's the difference. When this result is positive or negative infinity, then this is the vertical asymptote. But here, when you determine the limits at infinity, and if you get a number, not infinity, then that number is the horizontal asymptote. That's the difference between these two. Is that okay?
Yes, thank you.
Thank you. Did you want to pick a problem? Is that what you want, or just the difference between the two, or?
Yeah, I just didn't. I didn't really get the last question based on that topic that we just did. That's why I asked about it.
So you want to go back to the previous problem?
Yeah, the one with like the hole in the graph.
Right. So when the factor disappears, then there is a hole in the graph. If the factor does not disappear, then it's a vertical asymptote in this situation.